Hi, this is Roger from Kaika Labs, and today it's about two little tricks that you can do with your ATMega or with some of the AT-Tinies as well, and that is how the ATMega can measure its own supply voltage, and the second is how you can measure the temperature inside the ATMega, which can be equal to the outside temperature depending on how much self-heating you generate by loading the outputs of the ATMega. So let's start with the first thing, how to measure the supply voltage with your ATMega. And now your first idea would be, well, let's put the supply voltage, which we call VCC, to a voltage divider with, let's say, 1K and 4K, and this is of course a voltage divider of the ratio 1 to 5, which means here we get 1/5 of VCC. We lead this to one of the ADC inputs, which depending on which type of ATMega you have is the ADC input 0 to 8, and we compare this to the reference voltage, and the reference voltage can be set also to the internal bandgap reference, which is 1.1 volts BG. BG means bandgap reference, and well, now the relation would be simply the supply voltage that you want to measure is just 5 times because we have this voltage divider here, times the ADC value that you measure. This is the 10-bit value that you get from the ADC, from the analog to digital converter. I will call it ADU. This is the abbreviation for analog digital units. And you multiply it with your reference voltage, which in this case is 1.1 volts, and you divide that by 1024. This is equal to 2 to the power of 10 for the 10-bit resolution you get. So there are two things you have to watch out for. First of all, the internal bandgap reference has a is not very exact. The datasheet says that it is only 10%, has only 10% accuracy. That is, I think, the maximum value. But in all the units that I've ever gotten hold of, the typical accuracy of the bandgap voltage reference is around 3%. So that would be sufficient to discern if your batteries or your rechargeable batteries are empty, or if there is anything wrong with your supply voltage. And the second thing you have to watch out for is you have to set the reference input to the right bits, and this is here the 4 possibilities where what you can set the internal voltage reference to, and you have to use this setting for the bits ref S1 and ref S0, which are part of the ADMAX register. You have to use this, and then you get, as you can read, internal 1.1 volt voltage reference with external capacitor at the A ref pin. So this is the A ref pin, the analog reference voltage pin, And this, in this case, may absolutely not be connected to VCC or AVCC, the analog supply voltage, but there only should be a 100 nanofarad up to a few microfarads, however you want it, capacitor and nothing else. Otherwise, this doesn't work. In the Arduinos, the reference voltage is usually connected to the supply voltage, and then this thing here, this way to measure your battery voltage, VCC, doesn't work, but there is an easier and better way without using any external voltage dividers and without using any of the ADC, of the external ADC pin inputs. And that's perhaps the more interesting way. And now let's make a new diagram to show you this possibility. And as I just told, the analog reference pin in the Arduinos and many other circuits is connected to the analog supply voltage, and this also is tied to the supply voltage. So we already have one of the two things we need. We need a known reference, and we need to have a something to compare it with. And here we simply exchange the reference and the VCC. We take the voltage we want to measure as the reference voltage. And now there's a little trick with your ADC. From the datasheet you can see if you select not one of the external ADC inputs, but if you select in the ATMega register, if you select channel number 14, then you measure the internal bandgap reference. That means we don't have to use any external ADC pin, but we use channel 14, and now we measure the internal bandgap reference. And now, so we don't need any external components, and now the calculation to get your supply voltage is simply AVCC is equal VCC, because in according to the data sheet, the analog voltage is supply voltage is always connected to the digital supply voltage, and this equals the internal voltage reference 1.1 volt, as we have seen, plus minus 10% max, but plus minus 3% typical, times 1024 divided by the result of the analog to digital converter, so divided by the ADU value that you get. And it's as simple as that. No external connections. So the way to make it is, now you have to select AVCC with an external capacitor, which is always present at the A reference pin. So you have to set the bits ref as 1 and ref as 0 here in the ATMega register to 0 and 1. So the first thing is select AVCC with, okay, there should be a 100 nanofarad capacitor. It is already on board at the Arduino and usually all other ATMega circuits. Select AVCC with external capacitor at the A ref pin. Second, set the analog to digital multiplexer to channel 14. Third, measure your ADC value or the ADU value. And fourth, calculate AVCC equals the supply voltage, and that is 1.1 volt times 1024 divided by the ADU value. Simple as that. Sorry if I just put the piece of paper only now upwards, but now you can see the final result. So that was it for how to measure how the Arduino or any ATMega can measure its own supply voltage. And now let's take a look at how we can measure temperature. So as we go back to the data sheet with the different channels that the ATMega can measure, in this case, this is not possible with all ATMegas. This is the data sheet for the 48, 88, 168 and 328. But many other ATMegas also have this possibility. Just look carefully into the data sheet that you get, and here you will see at channel 8 there's a little note for temperature sensor. You just have to select channel 8, and then you get a result that is proportional to the temperature. There's only one thing you have to watch out for, and that is that in this case also you have to use the internal 1.1 volt Bandgap-reference as the reference of the ADC. So before we do the calculation how to get from the ADU value to the real temperature, let's make again a recipe how you can do it. You first have to select as the reference input, you have to select the internal 1.1 volt bandgap reference as the ADC reference. We have seen how this works also in the previous measurement situation where we wanted to measure the supply voltage. You set the bits refs as 1 and refs as 0 here to 1 and 1, and then you get the internal 1.1 volt bandgap voltage reference, and you connect, or if it already isn't connected, an external 100 nanofarad capacitor to the AREF pin, and you may not connect any other voltage to the AREF pin. That's important, otherwise it won't work. Second, you select channel 8, and that is the temperature sensor, the internal temperature sensor, and they give you in the data sheet some values. It is set that the measured voltage is going up for around 1 millivolts per degree Celsius or per Kelvin. And if you, they give you 3 examples of typical temperatures: minus 45 degrees Celsius, plus 25 and plus 85 degrees Celsius. And if you calculate, this is not exactly 1 millivolt. From here to here, I've calculated that it's around 1.03 millivolts per degree Celsius or per Kelvin. And from plus 25 to plus 85, it's around 1.01 1 millivolt per degree Celsius. So the slope of your temperature curve is not absolutely linear. And if you read further to the next page, they also tell you that there is, of course, an offset. The slope and the offset are not 100% correct. They tell you that they are only exact to around, without calibration, to a value of 10 degrees Celsius or 10 kelvins. In fact, again, the data sheet is on the safe side. What I have measured in units that I really used was an accuracy of around 1 degree Celsius, and I think that's quite enough for a simple measurement of the surrounding temperature. And you can do the math of your own, but I've done it for you, how you get the temperature in the unit of degrees Celsius. For our Fahrenheit lovers, please do the math by yourself. But we here in Europe, except for Great Britain, we measure in degrees Celsius, and that is simply the measured ADC value, which again I call ADU, the analog digital units, times 0.98 minus 262. It's as simple as that. And here if you want more exact values, this is the slope and this is the offset. And by twiddling around or adjusting these two values, you can get a more exact value. But be aware of that you only get the temperature of the chip, of the silicon, and not of the ambient temperature. And if you generate some power inside the chip, for example, by heavily loading the outputs or turning off all units in the chip, then of course the silicon temperature will be higher than the ambient temperature. If you know exactly what power is generated, if you have constant loads on your outputs, then you of course could correct the measured value for this additional offset. So usually, or not usually, always, the ambient temperature will be in fact be a little bit lower than the calculated value. But in my case, with a chip which had no heavy loads on the output, the result was within 1.5 degrees Celsius of the true measured ambient temperature. And I think that's really enough for a quick determination. For example, if your chip is heated up, you can even program in some routines that will, for example, protect the chip if it measures that it gets too hot. Anyway, a nice feature that the ATmegas can measure their own silicon temperature, and under special conditions you can also use this as a measurement for your ambient temperature, and perhaps or for example in any displays, in clock displays, etc. You can have an additional display of the temperature without an external sensor if you are if it's enough for you to be around 1 degree Celsius of the true value, or if you correct and calibrate your unit for slope and offset. So that was it. I hope you liked it, and perhaps it was inspiration for you to use the ATMega or the capabilities of the ATMega a bit more than before, and that you can save some components when using the internal temperature or the capability that it can measure its own supply voltage. That was it for today. Thanks for watching. Until next time, bye from Kanka Labs.